Guys, welcome back to our lectures on electrodynamics, and this is the third part of the fifth chapter that we're going to discuss today. Again, our main reference is Introduction to Electrodynamics by David J. Griffiths, and I recommend that you buy this book. So for this lecture, we'll discuss about applications of Ampere's law, and we know that the curl of B, because it curls around its source current, curl B is not zero. That's just mu sub O, or the permeability constant times the current density, and this is called the Ampere's law, and this is the differential form of the Ampere's law. So when you integrate with respect to an area, this term, it becomes this one. But we have Stokes' theorem that tells us that the integral of a curl over an area can be converted to an integral of just the vector here over the surrounding boundaries of the area, which is given by this, and that your BDL now is just equal to, of course, you're integrating this with respect to an area, so you have to also integrate this with respect to an area. So therefore you have by the way, this J.dA is, you're going to integrate the total current passing through the area, the cross-sectional area, and this is just the total current. So for example, if you have a loop and current is going in there, so you just calculate you just total the current here, total the current here passing through the area. So this is just the total current. So your Ampere's law is converted into integral form by this one. This is just like Gauss law. When you're able to see Gauss law in your mind, anyway, I'll just write it here. E.dA is equal to Q enclosed over epsilon sub O. So here you have an area enclosing a total charge Q enclosed. That's the Gauss law. Here you have a field. Here your field is electric field, and this one is magnetic field. Your field encloses this total current here, I enclosed. And of course, instead of the Gaussian surface, by the way, B does not enclose, but B curls this current here, I enclosed. Instead of a Gaussian surface for the Amperian law or Ampere's law, you have to have a loop DL, like here. So say for example, so if you have a current that's passing through here, and you just enclose it with a loop, so the most or the safest symmetrical loop is a circle. So you can enclose that, for example, with a circle Amperian loop. Then you'll be able to get the magnetic field. So in this Amperian loop, this is of course imaginary. So your Amperian loop will so in this loop you have say for example your current is going there, so your magnetic field will be going here. So at this point you have here, at this point you have the Amperian. In the Amperian loop, the magnetic fields are tangent. So that's the direction of the magnetic field, but the magnitude is constant in that Amperian loop. So of course, if your Amperian loop is much bigger, if it is bigger, then your magnetic field, of course, in this tangent to this Amperian loop is smaller. So smaller. Those are smaller magnetic fields. So that's about the Ampere's law. Let me clear the things here. So in order to resolve the direction of the magnetic field, always use your right hand. Do the right hand rule, and you always point your thumb to the correct direction of the positive current. So for example, if the electrons are going to the right, then the positive current there is going to the left. So you have to point your thumb going to the left. And so your magnetic field would be, in this case, if it's going to the left, then so if your current is going to the left here, then your magnetic field would have to be, the direction would be here. So that's the curl of your fingers using your right hand. So again, just like Coulomb's law, you have a counterpart of the Gauss's law. And for the Biot-Savart law, you have the Ampere's law to be able to get the magnetic field. But again, like Gauss law, Ampere's law in particular, you need appropriate symmetry of the loop, like circle, square, and as we see in the examples that we're going to discuss later. So for electrostatic, it's Coulomb's law, and then you have a simple method to calculate the electric field, which is Gauss law. And then for magnetostatics, you calculate the magnetic field by Biot-Savart law in general, but there's a simple method called Ampere's law to do that, exploiting this one here, exploiting the symmetry of the system. So by the way, this is, as I've discussed before, so you have currents here passing through the surface. The surface really not need to be a circle, but in general it's not a circle, but for Ampere's law you need to have a symmetric surface, and this surface must be bounded symmetrically by some loop. So let's start with our first example for Ampere's law. 5.7 example, find the magnetic field at distance s from a long straight wire, figure 5.32, carrying a steady current I. And this is the same problem solved in example 5.5 using Biot-Savart law. So here you have current I and you're looking for the magnetic field. We know that the direction of B is circumferential, circling around the wire. So in this case, you're using your right hand, you point your thumb to the left, to the right, to the right, and then the curl of your fingers will be the direction of your curling magnetic field. So your magnetic field will actually curl this circle. So that is your magnetic field. By symmetry, the magnitude B is constant around an Amperian loop of radius S centered on the wire. So the magnitude at each point in this circle here, the magnitude of the magnetic field is the same, but they differ in direction at each point. So anyway, let's look at the Ampere's law. So you have BDL, and then of course the magnitude is constant, so you can take this out of the integral. So this is just actually BDL cosine theta, but the DL and the B, so you're doing a circle, so this is your B, and this is also your DL. So the theta between B and DL is just equal to 0. So cosine 0 is 1. So this is just now BDL. From B.dl you now have BDL. And since B is constant in magnitude, you can take that out of the integral and just integrate DL. So the integral of DL, because that is just a circle, so your total length of this is just 2 pi. The radius is S, so this is just 2 pi S here. And then this is of course equal to mu times I enclosed, which is just I. So your B is mu sub OI, 2 pi over S. So in general, your B is a vector. So if this is a phi, if the direction is given by phi, then your B is equal to mu sub OI sub I times 2 pi over S phi. Now the second one is